Discrete random variables, the probability mass function and cumulative distribution functions. The objectives for this topic are to determine the probabilities from the probability mass functions and the reverse. Determine the probabilities from cumulative distribution functions and cumulative distribution functions from the probability mass functions and the reverse. The probability mass function. For a discrete random variable x with the possible values x sub 1, x sub 2, up to x sub n, a probability mass function is a function such that, first, f of x sub I is greater than or equal to 0. Taking note that this is a probability, its value should always be positive for all values of x. Second, the summation of f of x sub I for I is equal to 1 to n should add up to 1. And third, the third condition for a probability mass function is when obtaining the probability of the random variable x taking a value x sub I, it would just be f of x sub I, meaning we just plug in the value of x sub I to the function so that we can get the probability of x as x approaches x sub I. Let's have some examples about the probability mass function. The sample space of a random experiment is a set that contains the value a, b, c, d, e, and f, and each outcome is equally likely. A random variable is defined as follows. The possible outcomes are a, b, c, d, e, and f, and we associate this to a random variable x taking values x sub I equal to 0 for a, 0 for b, 1.5 for both c and d, 2 for e, and 3 for f. Since this follows equal likelihood of occurrence, we are going to apply uniform probability, meaning P of A is equal to P of B equal to P of Z and so on up to P of F. And since these are 6 equal likely activities, we will have the probability equal to 1 over 6. So the probability for the events A, B, C, D, E, and F would just be 1 over 6. Determine the probability mass function of x and use the probability mass function to determine the following probabilities. Note that A and B is under the random variable x having value of x equal to 0, and C and D falls on the random variable x equal to 1.5, and E is under 2 equal to 1 over 6 and F equal to 3. So we can have the probability mass function x equal to 0, 1.5, 2, and 3, and the total probabilities for f of x. 2 over 6, 2 over 6, 1 over 6, and 1 over 6. Now we obtain the following probabilities. First, the probability of x equal to 1.5. For the probability of x equal to 1.5, we're just going to consider this, evaluate f of x equal to 1.5 or f of 1.5. So we will be having f of 1.5 is equal to 2 over 6 or 1 over 3. For the second one, the probability of x in between 0.5, and 2.7. The probability of x in between 0.5 and 2.7, so it would be in between 0.5 and 2.7. So that would be f of 1.5 plus f of 2, which is equal to 2 over 6 plus 1 over 6, which is equal to 3 over 6, or 1/2. For the probability of x greater than 3, since there's no value of x greater than 3, so it would be an empty set, and the probability for an empty set is 0. Next, the probability of x is greater than or equal to 0, but less than 2. To solve for this probability, we take note of the values greater than or equal to 0, but less than 2. So it would be f of 0 plus f of 1.5, which is 2 over 6 plus 2 over 6, or 4 over 6, which is equal to 2 over 3. And lastly, for letter E, the probability of x is equal to 0 or x is equal to 2 is equal to f of 0 plus f of 2. F of 0 plus f of 2 would be equal to 2 over 6 plus 1 over 6, equal to 1/2. Cumulative distribution function. The cumulative distribution function of a discrete random variable x is denoted by the uppercase f of x is equal to f of x equal to the probability of the random variable x taking values lower or equal to x, which is equal to the summation of f of x sub I, where x sub I is less than or equal to x. For a discrete random variable x, f of x satisfies the following properties. First, f of x is equal to the probability of x less than or equal to x, which is equal to the summation of f of x sub I, for x sub I is less than or equal to x, which is the definition for the cumulative distribution function. And since these are just the summation of all the probabilities, the cumulative distribution function is always in between two values, 0 and 1. And if x is less than or equal to y, then f of x is less than or equal to f of y. The cumulative distribution function examples. Determine the probability mass function of x from the following cumulative distribution function. We have the cumulative distribution function f of x is equal to 0 when x is less than or negative 2, 0.2 when x is greater than or equal to negative 2 but less than 0, 0.7 when x is greater than or equal to 0 but less than 2, and 1 when x is greater than or equal to 2. We can plot its histogram, or we can plot its ogive as this one. 0, 0.2, 0.7, and 1 along the interval less than or equal to negative 2, from negative 2 to 0, 0 to 2, and greater than 2. To get the probability mass function, we're going to subtract two successive cumulative distributions. So we have 0.2 minus 0.2 equal to 0.2, 0.7 minus 0.2 equal to 0.5, and 1 minus 0.7 equal to 0.3. So we have this one. So the probability mass function is equal to 0.2, 0.5, 0.3, when x would be equal to -2, 0, and 2 respectively. As a summary, the probability mass function provides probabilities for the values in the range of a discrete random variable. And the cumulative distribution function of a discrete random variable x is denoted by capital F of x, which is equal to f of x, which is the probability of x less than or equal to x, which is the summation of f of x sub I, for x sub I is less than or equal to x. Try this as your activity. These are the answers.